Tonight, on a very special edition of Inside Ashland, the brand new Regional House Street Water Treatment Facility. The new $10.8 million water treatment plant is up and running. Right now, the water being pumped into your house is cleaner and better tasting than ever before. Now, we will take you on an inside look at the construction and the operation of the brand new facility. If you've been relying on bottled water like many of us for a long time, you may want to stay tuned and find out if this water supply is even better. All of this and more on this edition of Inside Ashland. Most people take for granted that when they turn on the faucet, they will get clean and drinkable water, never giving it a thought to where that water comes from and how it gets there, until, of course, there is a problem. Through the years, Ashland residents have experienced a number of problems with the water. One of the most obvious problems was when the water was discolored. In Ashland, this was caused by iron and manganese sequestration. Iron and manganese are often present in groundwater at levels that can discolor the water or cause it to take on an unpleasant odor or taste. Although the water may still be safe to drink, treatment is often desirable. Our treatment consists of adding polyphosphates to the water. Another problem facing Ashland residents was a corrosion control problem, and that was due to old pipes in town. This problem became worse as the town population grew and more new homes came online. In 1994, the Department of Environmental Management sent out public notices to all Ashland residents to boil water before drinking. Now, this was due to a discovery of bacteria in the water supply. A chemical reaction between the bacteria and the chlorine created high levels of trihalomethane, otherwise known as THM. Chloramine was added to reduce the levels of THM in the water supply in June of 1999, bringing the town into compliance. Although the chloramine has been deemed safe for most people, chlorinated water can cause problems for people on kidney dialysis. In addition, chlorinated water can be a problem for fish kept in tanks, aquariums and so forth. Not only did Ashland need to improve its water quality, but they also needed much more of it due to the major increase in its population. In 1998, the Ashland Town Meeting voted to construct a state-of-the-art water treatment facility at the cost of $8.8 million. The final cost of this treatment facility is $10.8 million. Construction began in August of 2000. The two major components of the job are the building of the plant, of course, and the two lagoons located across the street from the plant. Ashland's water supply and distribution system includes over 90 miles of water main and 6,010 individual services. The system serves over 15,000 customers and provides fire protection services through 766 fire hydrants. In the last 12 months, the department produced and delivered over 512,180,000 gallons of water to the distribution system. Now that's an average of 1,399,000 gallons each day. The system also maintains over 6,600,000 gallons in two reserves. One reserve is located on Cedar Street and the other one is off Woodbridge Lane. This storage allows us to meet peak system demand and also maintain an adequate supply during fire pumping activities. That water is drawn from wells located at the water treatment plant on Howe Street. The water plant is built adjacent to the Hopkinton Reservoir. The reservoir is a man-made lake 75 to 80 feet deep. According to geodetic information obtained by the Water Department, the lake holds over 1 billion gallons of water. The dam was constructed in the late 1800s by the MDC. The dam is over 80 feet tall. It was constructed from local granite and concrete. The reservoir was originally intended to be an additional water source for Boston. Today, it's a mixed-use reservoir. The dam is used for flood control and as a recreation area for swimming and boating, as well as a drinking water source due to the fact the plant utilizes groundwater rather than surface water from the reservoir. The groundwater is pumped up from wells 30 to 40 feet below the surface. After the water is drawn up from the wells, it goes through the first stage of the treatment process. Now, the first step is to treat the water with ozone. This is a new way of disinfecting the water. The plant generates ozone by combining liquid oxygen and electricity. Bill Nunnery, project manager for EarthTech, gave us a tour of the ozone generation area early in the construction.
This is the new ozone room. You'll notice it's about 80% complete in here now from the piping. This is all 316 stainless steel. The ozone's such a strong oxidant we have to build in stainless steel. And these are all pressurized tanks. So the water's coming out of the well. We're generating ozone here on site in a high concentration and blending it in with the high flow and then giving detention. All in pressurized 316 stainless steel vessels. It's running about 30 pounds of water pressure at this point in the process. A little bit darker this here. This is the filter room, which is really the heart of the treatment plant. In the center basin here is the contact clarifier. The water will come into the bottom of the contact clarifier and then flow up. When it reaches the top of the contact clarifier, all the color will be removed from the water. We'll then go into the piping gallery we saw downstairs. And this is the filter bed here. There's going to be 12 inches of sand and 6 foot of granule activated carbon placed. The water will then flow through the granule activated carbon. 12 inches of sand. It's quality checked, and then it will fall. It will then have chlorine added to it. It will go to an implant clear well that's 15 feet deep underground, under the plant. And from there, it'll be pumped up into the towns of Ashland and Hopkinton. The two towns actually have separate pressure planes. The water will leave here via one pipeline to Ashland, about 100 pounds of pressure. The other pipeline and pumps will go to Hopkinton at about 140 pounds of pressure. I want to show you the control room now. Have everything shut, the wires now. Let's see. Is there any lights in there at all? This is the control room. When the plant is done, there's going to be a window looking out over the filters. And all the pumps, every valve, every flow instrument, every indicator is wired here back into the central computer system. And as you can see, they're just in the process of pulling the wires and tags. It takes about 6 weeks. Each wire has to have its location verified and signal tagged. It takes about 6 weeks just to complete the terminations after all the wires are pulled. And we're still here in the pulling stage at this point.
My name is Stephen Small. I'm the resident engineer for EarthTech, representing the town on the design and construction of this water treatment facility. I've been on site since August of 2000 when we did our groundbreaking and began the excavation for the building. And an update to where we were roughly 6 months ago when the project manager, Bill Nunnery, reviewed progress for you. You can see the well houses behind us. We have some existing well houses that are just now being ready to be updated. As the plant was run, we were producing water from these two existing well houses, which are two of three wells that the town has been using for a number of years. These wells will now need to be updated to perform properly with the new plant. The wells themselves will contain brand new pumps. We've got some pumps laying on the ground. These light green tubular sections are the new well pumps. The new wells, number 7 and 8, have been used to start the plant. Those are brand new wells, new casings, new everything. And we are taking water from wells 7 and 8 so as not to interrupt the current water supply to the town of Ashland. And as the procedure is written, once the state accepts the plant as running within the tolerances required by the state, the wells 4, 5, and 6, the existing wells, will be taken offline, updated, and put back online. As one of the project's tasks to be completed is the installation of new wells and new pumps in the existing wells, Well number 6, which we're standing in front of, and you're looking at the replacement pump for well number 6. Previously, the wells pumped out to the tanks on Cedar and Woodridge Road. Those tanks are higher in elevation and require more horsepower to push the water up to those tanks. Now that the new plant has new high service pumps which will do that work, the amount of horsepower needed to pump the water from below where we're standing into the treatment plant for processing is diminished. So to make use of any energy savings possible, the wells have been updated with high efficiency pumps. These pumps have a dramatically lower horsepower because they don't have to push the water as far or as high to get it to the plant. These pumps are shipped from Tulsa, Oklahoma. We've got 12 new pumps in the building. We've got backwash pumps which clean the filters. We've got high service pumps, 4 high service pumps for Ashland, 2 high service pumps for Hopkinton, as well as 5 pumps for all of these new and old well houses. And there's a couple of smaller pumps which will pump the water up the hill, processed water, to be recycled. So there's quite a few pumps in this place and a lot of horsepower involved. These are vertical turbine pumps. There'll be an electric motor that's mounted after it's installed. An electric motor is mounted, but as you can see this shaft, what they'll do is they'll take a crane and they'll take the vent off of the existing well number 6. That's a vent and a hatch. They'll pull that off, they'll lower the crane ball inside, hoist out an almost identical unit of higher horsepower. It's seen a pretty good amount of its service life, so it's not being wasted. The town is actually going to recycle those well pumps and use them in other locations. Once the well pump is taken out, this new vertical turbine pump will be literally slipped right down in its place and bolted up, and a 100 horsepower motor will be bolted onto the top. The electricians will connect the thing up. The piping will be virtually identical to what's in the ground now. The only replacement part is the pump itself. We have 3 more pumps, well number 6, well number 4, and well number 5. Because of the process and the acceptance of the plant, we have to wait until the plant is accepted before we can take 4, 5, and 6 out of service so that we don't leave the town without a backup. Presently, wells 7 and 8 will pump a maximum of 4 million gallons a day. The town uses approximately 2 million gallons a day, depending on the need, the temperature, the water demand, and whatnot. So 7 and 8 are, one is a backup to the other. So that's the minimum amount of pumps this plant can be run on. And these are additional pumps which allow us greater flexibility and also greater capacity. I mentioned we only have 2 million gallon really usage now. We're going to be sharing up to 1 million gallons a day with Hopkinton, and those usages will increase over the amount of years. So we've got virtually double the amount of capacity, well capacity, that we originally had. So this plant is built for the long haul. We're going to get a lot of years of service before there's going to be any additional water sources needed for Ashland. Behind me you can see a 6,000 gallon oxygen tank. The oxygen tank is the primary chemical used in the ozone production. Ozone is produced inside in the ozone room. We'll show you how that works. The ozone is used to remove odor and color. It oxidizes the manganese, which is one of the natural ingredients found in the water. Many of you people notice it probably as brown stains. That's manganese, potentially some iron. This changes the chemical makeup of the manganese and allows the manganese to be removed from the water in a process called flocculation. So the ozone oxidizes the manganese. The water is then adjusted with chemicals, and the flocculation and the coagulants take out any other particles, almost visible particles. If you were to take a clear bucket of water out of the lake or out of the pump, you might be able to notice some slight discoloration in the water. And you can imagine with a large volume, your volume of discoloration would be larger. That's a primary problem here in Ashland. There is some taste, there is some odor problems people have been complaining about for years. This system is going to handle that. It's going to allow us to remove the manganese and give a nice tasting water and a better looking water, both for your laundry and also for your in-home appliances. We can go inside and we can have a look at the actual ozone system. Ozone system is made up of a number of tanks. A basic nutshell explanation is that the ozone is brought in. The water is literally running through piping underneath us from the wells. The first thing it contacts is ozone, and you'll see when we go inside there's large tanks. They're called ozone contact tanks. And the ozone is mixed with the water, which causes that reaction I mentioned. After the ozone contacts the water and it's oxidized, the ozone is then removed from the water and it's run through a destruct unit, which basically heats up the ozone and breaks it back into its oxygen parts, and it's emitted to the atmosphere just as raw oxygen, a pretty harmless substance that we all breathe every day. You might have noticed the no smoking sign. Liquid oxygen is highly flammable and explosive. I can assure you that the regulations require that all possible safety measures are in place, both in operating parameters, safety shutdown procedures, and safety interlocks to not allow any of this oxygen to become a hazardous problem, whether by explosion or by overdosing the water. There's a system of sensors which will shut down in the event that the ozone into the system is too high, or in the event that there was a leak or something which would cause a safety hazard. So those things are all figured in the design and construction of the plant. So why don't we have a walk inside and have a look at the ozone. Well, now we're inside the plant, and we're going to walk through in a path that the water actually follows. The green pipe that you see above me contains the raw water or partially processed water. We're standing in front of the ozonation room, which is where the ozone is added to the water to oxidize the manganese in the iron. The way it happens is the water comes through the raw water piping from the wells. It's brought up into the two contact tanks, these two large tanks. The water flows in. contacts the ozone. The ozone is removed. These destruct units heat up the oxygen, break it down into its original parts, and it's exhausted out through the wall into the atmosphere as harmless oxygen. These two cabinets are the ozone generators. They literally combine the oxygen. Oxygen is O3, 3 parts of oxygen. And these are two redundant generators. One can serve as a backup to the other. We have two systems, 110 and 120. We can run off of either or both depending on the amount of flow we're producing. The water follows along. It's been ozonated. The water follows along in a semi-raw state. It's now had the initial process of ozone. This yellow unit you see above me is the static mixer. If you look back slightly, you see a number of hoses all labeled with different chemicals on them. Some are dark, some are light. Those are pre-coagulant chemicals. They are used to clean the water. For instance, the ferric chloride, which is the reddish color hose you can see, that is a coagulant. A coagulant serves a function of literally grasping the dirty particles from the water as it flows through, and it gets captured in the filters, and the ferric chloride is filtered out. What is left is pristine water. That water goes on to another filtration system, and then it is stored in large tanks below the floor, which will eventually be pumped to either town upon its request. Some of the other chemicals we're looking at here, we have polymer. I mentioned that we have coagulants. Polymer is one of the coagulants. Again, that's a chemical used to grip contaminants, not really contaminants, but grip naturally occurring particles, minerals that are in the water. These coagulants adhere to those particles, and the coagulants are larger than the openings in the filters, and as the water runs through, the coagulants and those particles are caught in the filters, and the clean water comes out the other end of the filter. So that's a quick breakdown of how the chemical process works. The water flows through. Why don't we take a walk into the pipe gallery? Okay, so we're here in the pipe gallery, and we're following the piping along as it leaves the ozone room, goes through the static mixer where various coagulant chemicals are added, to what is called the raw water. And as a quick explanation, the raw water is as it occurs in nature. The water is drawn from a well 30 or 40 feet below the earth in a raw condition. That condition contains naturally occurring chemicals. Manganese and iron are two of the chemicals that we're working to eliminate here in Ashland. The water runs through the piping system into this pipe gallery, and this is the heart of the filter system. The raw water comes down into a system of pipes which distributes the water to 4 different filters and 2 different clarifiers. It looks quite complex. In reality, it follows simple logic. There's 2 banks with a clarifier in each one. Clarifier is an initial filtering system. The coagulants, which are now at this point attached to the naturally occurring particles and minerals, go through the clarifier, which has a garnet stone, a very fine pebbly stone you might see in somebody's driveway, or even finer. It looks very normal, very average looking. Water is forced through those clarifiers. The coagulants is almost like a gummy ball now of chemical with these naturally occurring particles attached to it. It runs through the clarifier, which captures these gummy balls of naturally occurring particles, and as the water flows out of the top of the clarifier, it runs down into a common header, and then it can be distributed into any one or all of the filters. The filters are a finer material. It's an activated carbon material, which is quite a bit finer than the garnet used in the clarifier. So any contaminants or any particles which are still free floating that have not been captured by the clarifier go through 6 feet of activated carbon and 18 inches of sand, literally drawing the water through, leaving these small, very fine particles in that sand and carbon. What comes out below is virtually what you drink. The clean water comes out at the very end and runs into a clear well, which is underneath the building. It holds 550,000 gallons of water. That is the source of stored, treated water for the town. Whenever the filters run below, whenever the tanks, the clear well runs below the 550,000 gallons, there's a series of floats and signals that are transmitted, and it tells the plant we're down to X level, begin making more water. The water is more or less made on demand in response to the amount of water pumped out to the tanks out on Woodridge Road and Cedar Street, which is where you draw your drinking water from overnight. Here we are upstairs in the filter area. Here you can see the open side of the tanks, which actually hold and process the water. The center tank is what we've been referring to as the clarifier. The clarifier, again, grabs the particles, the initial cleaning, and runs them through. On either side is a filter. And the operators are going to run through what's called a backwash sequence. Minimum of every 4 hours, the flow is reversed in the clarifier, which releases the particles which have been captured with the coagulants on them. It reverses them, and it's flowed into a tank, the backwash basin. And new clean water is then processed through, which allows another 3 to 4 hours of water processing prior to going into the filters. Right now you're looking at one of the filters. The water is actually, you can barely see it flowing, but these filters are in process and the water is being processed as we speak. Now, go ahead, why don't you film that? Here we're watching the water level in clarifier 220 drop. In a few seconds, air and a water mixture will come on to stir up the coagulants that have been captured in the garnet media. You'll be able to see some of the stuff that comes out of the water. The water drops to a level of the troughs. The troughs is where the water exits into the backwash basin. What's happening now is the water's draining out. New water is coming in. Air is being introduced. The air literally loosens up the particles, loosens up the garnet, and allows the contaminants, the iron and manganese, to be loosened up. You'll notice the discoloration. That is the combination of coagulants and naturally occurring minerals in the raw water that are being captured by the clarifier. As we mentioned earlier, every four or so hours, the water in the clarifier is cleaned by reversing the flow and adding the air to loosen up the particles. This will run through a whole process. Then the water will calm down. The air will be shut off. There'll be an elapsed time. There'll be a delay so the water can settle out and get to a point where it can begin processing again. Makes you thirsty just looking at it, doesn't it? It is concentrated. It's concentrated sediments and a combination of the coagulants, the chemical coagulants, but the discoloration you see, a good portion of that is a naturally occurring iron and manganese, which is a dark brown and tan color in the natural environment. And many of you may be familiar with this from your laundry or from your bathtub. And you shouldn't see this in your water anymore. You should see nice, clean, processed, filtered water coming through. Now in the filter control room, this is the brains of the entire operation. There's a control panel and there's a SCADA system. The SCADA system is a supervisory control system which allows control of this plant from backup computers and from laptop computers remotely to operate or to monitor the system. This system is a redundant system. Computers have been known to have problems. So the system, the basis of the system is a touchscreen system, which is the heart of the entire system. This system is literally a touch screen, and all the different filter controls and processes, as you can see, are on here. System status, everything that happens in the filter control process occurs in this panel view. That panel view can also be used from a remote location from the SCADA system. And the SCADA system is a very complex arrangement which allows us to monitor all of the procedures that are going on from multiple locations. This particular screen we have up now is the overview of the filters and the clarifiers we were just looking at. We were watching clarifier number 220 backwash. You can see right on the screen that this is cleaning itself. So what happens out there happens on the screen at the same time. The clarifiers are flanked by two filters. There's constant analyzing of the water quality is going on. What you see here, this 0.01 NTU, is what's called a turbidity reading. The turbidity in layman's terms is cloudiness in the water, the discoloration, and that is limited both by the state and by the town's requirements as to how clean and how clear they want the water. These levels run anywhere from 0.3, which would stop the plant. 0.3 is unacceptable, down to 0.01, which is very clean. Right now you can see the water we're processing is very clean. 01, 04, 05, 06. The water is we're in good shape as far as the water goes. These different color valves, these little butterflies look like. The green is a valve that's not in service. The red is a valve that is in service. You can see that the clarifier we're looking at, these red valves, allowing the water to flow out, and it eventually makes its way back into the backwash basin. Whatever happens out there can be controlled or observed from the SCADA system. The SCADA has a hot backup, which is in the existing chemical feed building. So in the event of a lightning strike or just a malfunction in the computer, the operators have the option of going downstairs and getting on another SCADA computer to do any kind of adjustments they may need to do. Or in the event of even more of a failure, they could come up and use the touch screen that we were looking at earlier. We were out in the plant, we were walking around, we talked about the wells. This is the screen view of well number 8. The well, you can see the well starts at 268 up to an elevation of 307, which is roughly the ground level. This tells us exactly where the water is in the well. As the summer goes on, the upper level will slightly go down as the reservoir, some of the water in the reservoir evaporates. There is no fear, no problem that the water would ever get to a point where we would not be able to pump out of some of these wells. The water is regulated, however, at certain levels. They do not allow the operation of all the pumps. Earlier we talked about the elevated tanks. This system is set up to operate on a tank signal. The tanks have, the large one is located on Cedar Street, and the smaller tank is on Woodridge Road. Basically, how the town operates their system is, in the morning is a high demand for water. The operators start the plant. The tanks which have been used overnight, the water may be down slightly lower. The signal is sent saying we could use some more water in the tank. The pumps turn on, they fill the tank up. When the tank achieves a certain level, it will turn off. So the actual request for the water by the system comes from the tanks. So in the event that the plant is shut down overnight and there has been a fire or a water main break and the level in the tanks is actually lowered down, this will signal this plant to turn itself on regardless of operators being here or not, and will fill the tank back up to maintain that emergency buffer that we always have to have, and also just in general purposes to keep the water full for the morning rush, which is the biggest time for water usage is in the morning. So that's a quick overview of how the system works.
I was just about to ask about the tanks.
Either filter train, they're identical, they're interchangeable. Presently we're running through both of them. Well, here we are in front of the analyzers. There's a number of different analyzers which perform different functions. They check the water for turbidity, which we mentioned is a cloudy appearance in the water. These meters read the turbidity and they respond back to the plant. The plant is actually controlled by the turbidimeters in one sense, that if the turbidity is too high, that means the water is a little too cloudy for our requirements. It turns the plant off, probably backwashes something to clean it out, and we'll put it back in service. These filters you're looking at, these turbidimeters you're looking at, are reading actually very good numbers. This 0.061 is quite low. The requirement, the cutoff requirement is 0.3. So as you can see, we're very low in turbidity, which means the water is exceptionally clear as it's being processed. We check chlorine. Chlorine is introduced just before the water exits the building to kill any bacteria. And the chlorine by law has to be analyzed. There's only a certain amount of chlorine that's allowed in the system by mass regulations. So we analyze the water in numerous different locations and fashions as it comes through. This meter here is a pH meter. pH is the acidity level in the water. Anybody who has a swimming pool is probably familiar with pH in your little test kits. This meter actually does that all in one, and it reads the this particular one is clear well effluent. The pH is adjusted in an effort to reduce corrosion. Too high of a level of pH could cause some of the piping in your house to leach lead from the old solder and whatnot. So the pH is regulated just as the turbidity is regulated to produce an acceptable water to the homeowner, as well as a water that's not going to disrupt their plumbing fixtures. So the water runs through these. You can see water behind here, and the water is running through. This water is constantly analyzing. There's an electronic eye in the pool of water here, and it shoots through this constantly moving water and analyzes it for the turbidity. This particular is the combined effluent turbidimeter, which means all of the water from all of the filters meets and is tested through this turbidimeter. And you can see we have great turbidities. They're nice and low. It's just as we've designed, and the process is running fine as we see it right here. These analyzers run around the clock. Whenever the plant is running, they're constantly running and feeding back to the SCADA system, giving it the data, telling it if it needs to be adjusted. The operators can look with a click of a mouse and tell what any chemical is. They can click in on any of these analyzers, either remotely or from the control room upstairs, and get a feel for actually the exact quality of how their water is going. It's quite a complex system. These green pipes are sample pipes. This water is sampled raw, pre-coagulated. It's sampled in through the filters, and it's sampled as it leaves, which is the combined. And so these pipes are all individual analyzers, which help us keep track of the quality. Okay, here we are up at the lagoon area. The lagoon is a collection area for the processed water that's used within the filtering system. After the water with the coagulants runs through the water, and the natural occurring minerals, manganese, are captured within the filters. That water periodically has to be processed to clean the filters. They reverse the flow in the filters, which is called the backwash, which we reviewed. That backwash water is held in a separate tank because it's got some naturally occurring particles as well as the leftover coagulants. That material is pumped up the hill and can be divided into one of two of these lagoons that you see here. It's a system of valves that allows us to alternate between lagoons. As everything else is designed in this plant, there's redundancy. So one lagoon can be online and one lagoon can be taken offline for servicing. The only servicing would be to clean out any collection of materials, minerals and whatnot, and coagulants that will eventually collect in the bottom of this lagoon. The water from here runs through these slide gates, is metered downhill, and then that water is released back into the lake. So I hope that concludes an explanation of where we've been, where we've started, and where we've ended up in the year 2002. Our drinking water, which originally came from the ground, still comes from the ground, but is now accented with high technology to provide a high level of security and a high level of purity to the drinking water that you receive when you turn on your tap here in Ashland.
After many years of problems with our water source and waiting for a solution, Ashland residents can look forward to very clean, drinkable water with our new state-of-the-art water treatment plant. The new House Street facility is now online at Ashland, so let's all drink to that.